on a billiard table, a white ball strikes a red ball. White ball, red ball. Okay. That was at rest before collision. At rest, okay. Arrow, no arrow. Makes sense. After the collision, both balls are observed to move along the same line. Two arrows showing some sort of ambiguity, and red ball moves to the right. Okay? The speed of the white ball before the collision is 2 meters per second. So 2 meters per second. And after the collision is 0.3 meters per second. But the direction is ambiguous. So that's a speed, not a velocity. Speed of the red ball after the collision is 1.7 meters per second. Okay, the white and red balls have the same mass. Okay, for this set of equations, the billiard balls are sliding on a frictionless surface. Frictionless surface. Okay, so first question is, collision was elastic, inelastic, or completely inelastic? So this is a question of definitions. So momentum is always always conserved. So P initial equals P final. Now kinetic energy for the ball, energy is always conserved, yes, I know. But for the balls, in this case, sometimes kinetic energy is lost to some internal friction or sound or radiation or something else is produced so that the two balls don't have the same kinetic energy. That's an elastic collision. The way I remember it, the mnemonic is you have E here, and so that means that energy kinetic is conserved. So E for energy kinetic, conserved. And then inelastic is just the other one where there's not a conservation of kinetic energy. But the momentum is conserved for all of them. And then when it says completely inelastic, think of this as two pieces of clay. So one clay hits another piece of clay, and we have a combination piece of clay that goes off into the sunset. So the question here then is energy kinetic conserved? And we can sort of maybe tell that. We'll figure this out. So we'll assume it's conserved. So it'll be energy kinetic initial, energy kinetic 1 initial. This will be 1. This will be 2. Plus energy kinetic initial. These are i's. Of 1. Yeah, we're good with this. I should do 1 and 2. There you go. Nope. My notation just got terrible. Okay. Focus. So 1, this guy, initial, plus energy kinetic 2 initial equals, question mark, because we're not sure, energy kinetic 1 final plus energy kinetic 2 final. There we go. In this case, energy kinetic equals 1/2 mv squared, and we're told they have the same mass. Yep, the two balls have the same mass, which is convenient because that way we can then cancel the masses. That sounds like a very politically charged statement. Cancel the masses. Maybe you can find that in the Communist Manifesto. No, maybe it's, I don't know, proletariat? Okay, focus. 1/2 mv1 initial squared plus 1/2 mv2 initial squared equals 1/2 mv1 final squared plus 1/2 mv2 final squared. So this is the same equation right here. I just wrote it out in a longer form. Ideally, I'd have mass 1 and mass 2. So I guess, okay, I should put those in 1, 1, 2, 2. But we know they're all the same. So we'll divide both sides by masses. This is actually more of a question mark there. So all the masses can go away. All the 1/2s can go away. We know that the 2, the red ball, is initially at rest. So V2 will be 0. So this will go to 0. And we are left with V1 initial squared equals, question mark, V1 final squared plus V2 final squared. Okay? So we know the initial speed is 2, so it'll be 2 squared. 2 squared equals, question mark, 0.3 squared So, and for that, we don't care about the direction because it's positive, negative, doesn't matter. When you square it, it loses its sign. Plus 1.7 squared. Okay? And looking at this with a calculator, we have clear. I'll do the left side first. 0.3 squared plus 1.7 squared. We get 2.98. That's not very much. 2.98, which does not equal 4. So there was a loss of kinetic energy, and that means that it was not elastic. The two balls did not stick, so they were not completely inelastic. Therefore, we'll call this an inelastic collision. In reality, pretty much everything is going to be inelastic. You can just get really close approximations to elastic. Okay. In what direction is the white ball moving after the collision? Okay, so this is going to use the concept that initial momentum, P for momentum, will be final momentum. And for that, we will write out, let's do mass 1 V1 plus mass 2, these are initial. M2 V2, also both initial, will be mass 1 V1, these will be final, plus, and these are velocities, meaning the vectors. Should probably do a little vector up top. I won't, it's assumed. M2 V2 final. Okay? Simplifying this, we know that V2, the red ball, is initially at rest, so V2 is 0. We know the masses are all the same, so we can divide by the masses. And so we are left with 2 equals 0.3 plus 1.7. Where this is plus or minus because we're not actually sure of the direction here. See the double arrow up here. So, looking at this, it might be obvious, might not be. This equation, before we use the question mark because we weren't sure kinetic energy was conserved. Momentum, on the other hand, always conserved. And so that means that this equation is true. So for 2 equals, I'm going to do plus or minus 0.3 plus 1.7. For this to be true, it has to be plus. Negative can't work because then we get 2 equals 1.4, which is not true. So we know that it's plus 0.3, and more importantly, it means it's the same sign as 2, the initial velocity, and the velocity of the red ball. So it means this arrow going in the same direction is what it's going to be. So we're going to call that plus x right here. Oh, plus x, plus x, plus x. So what direction is the white ball moving after the collision? Plus x. Okay, not too bad. So basic idea here is in collisions you have elastic, inelastic, elastic, starts with an E, therefore E, energy, kinetic, is conserved. Inelastic, kinetic energy is not conserved, but in both cases, momentum is always conserved. Yeah, it sounds good. Then we just write out the equations. You can jump and skip steps as you feel appropriate, or as you're panicking for time, jump steps as required just to finish in time. But be careful that when you start skipping steps, you're going to make more mistakes. And that's just kind of a trade-off you're going to have to make. Okay, on to the next problem. The experiment is repeated. The white ball has an initial velocity of white ball, maybe, is 2 meters per second. So this one, I'm going to write this up. 2 meters per second. I think it's the same as last time. In the x direction, but strikes the red ball slightly off center. Check. After the collision, the white ball travels in the positive direction at theta equals 13. So this will be 13 degrees. With respect to the positive direction, and the red ball travels in the negative y direction at an angle of 17 degrees. With respect to the positive x direction, as shown in the figure above, the speeds of the red and white ball after the collision are not known. Bum, 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 and cannot be assumed to be the same as in the first experiment. Okay, that seems fair. Compare the speed of the two balls after the collision. Okay, so we know that momentum is conserved. Specifically, it's conserved in both the y direction and x direction. So I'm going to start off by saying that momentum equals momentum. or momentum initial equals momentum final. So I'm going to say that, let's see here. I'm going to call the white ball 1 and the red ball 2. So mass 1, V1 initial, and these will be in the X direction, plus mass 2, V2 initial in the X direction will equal, I know my M's are terrible, mass V, these will both be 1s, these will both be 2s, these will now be finals, and this will be still in the X direction. Okay, so now we're just looking at the X direction. Ooh, maybe I should look at the Y direction instead. Actually, that's exactly what I'm going to do. I'm going to start by looking at the Y direction. Sorry, I know I spent all that time writing up those 8 X's, and now I'm crossing them out ineffectively because X already looks like a cross. We're going to go in the Y direction. Okay, so now we're going to start looking at what we know here. So we know that the red ball is initially at rest, so its velocity is going to be 0. We know that the white ball is moving horizontally, so its initial momentum in the Y direction will also be 0. We know that this can be looked at as a triangle, like so, where this is V1 final Y, which is V initial. So we're looking at just the magnitudes here. So this is going to be, and the masses can cancel. So we have, yes. So we have V initial 1 times sine of 13. So we have, this is going to be 13 degrees. Yes. And then for 2, this will be 1, this will be 2. This will be minus V initial 2. V initial? V final. There we go. That's probably better. V final. My notation is getting a little bit messy. That's what I get for having like 4 different qualifiers for each variable. Okay, this will be sine of 17. So really you could say that this is the sine of negative 17 degrees, but since sine is an odd function, you could just take that negative, move it to the outside. This equals 0, so we can set them equal to each other. So we have V final 1 sine of 13 equals V final 2. There we go. Final 2 times the sine of 17. So intuitively, this is going to be bigger. This is going to be smaller. And so for them to be equal, VF2 magnitude is smaller than VF1. Because big times small will equal small times big. Just intuitively speaking. So, actually, I'm going to make sure real quick. I'm totally 100% sure that the sine of 17 is bigger 0.292. 0.292. Now I'll do it of 13. Sine of 13. 0.225. 0.225. Okay, so the second one, VF2, has to be bigger than... Is that true? Smaller. VF2 has to be smaller. Okay, so this one, small, big. I'm kind of lost in the notation, so I'm going to be extra careful here. So this is asking for VWA. So this is the white one. This is the red one. W red. So white one is bigger than the red one. So white one right here bigger than the red one. So they're not equal, we know that. And they're asking which one's bigger. So velocity of white after is bigger than the velocity of the red after. And the reason that is because they have to have the same, or I guess the opposite, vertical components for their speeds. And since the white one is going at a shallow angle, it has to be going faster to compensate for that shallower angle than the red one does. Okay, so now we got that, and we have this data up here. Next question is going to be, what is the speed of the red ball after the collision? Okay, so this is going to be using our triangles and this data we have right here. So I'm going to erase this, erase this, probably even erase this one right here. And first we looked at the y component using conservation of momentum. Now we're going to look at the x component. So I'm going to go through the same process as before, but I'm going to skip some steps here. So we know that all the momentum for the system here is going to come from this initial white ball. So I'm going to call that V1 initial. And I'm going to leave off the mass because they're all the same, and we just cancel them out. So that will have to equal V1 final plus V2 final. And these will all be in the x direction. And we can rewrite this V1 and V2 using cosine. So this is V1 final cosine of 13 degrees plus V2 final in the x direction. No, just overall, times the cosine of 17 degrees. Before we use sine because we're dealing with y, this time we're going to use, first time we use sine because we're dealing with y, now we're using cosine because we're dealing with x. And I'm going to get those numbers up real quick. So cosine of 13 is 0.974. 974. Cosine of 17 is 0.956. 956. Okay? And so what we're going to do then is we're going to, because we know this one, this is 2 right here. The initial speed is 2. And we're going to be looking for the speed of the red ball, which is number 2. So we want to find this, so we'll solve for V final 1 and substitute that in. So V final 1 equals V final 2 times the sine of 17 over the sine of 13. Okay? And I'm not gonna use these numbers that I put up because they're good numbers, but I think we can go a little bit more accurate. And they'll be close enough that I don't want to mess with the okay, 17 over 13, and we get 1.2997. So I'm going to call that 1.3 equals 1.3 VF2. So coming up here, we have 1.3 VF2 cosine of 13 plus VF2. I know, my notation's going quickly downhill. Cosine of 17. So if we factor out the VF2 here and rearrange things, so I'm going to move this out of the way. Whoop, there we go. Ooh, green, blue, light blue. There we go. So we have the final velocity of 2 times 1.3 times the cosine of 13 plus the cosine of 17. That seems right, seems reasonable. And we know that'll equal 2, our initial velocity. So solving this, we have 2 divided by quantity, this will be a big one, 1.3, and not really 1.3, it's like sine of 17 divided by sine of 13, times cosine of 13 plus cosine of 17. Close. I think I need another parenthesis. We'll see what happens. 0.9. Yes, I'm good with that. 0.9. And this will be meters per second. Will be final velocity 2. Okay? Nope, and I messed up something terribly. Nope. Wait a sec. This one right here. Whoop, oh. I can draw that a little bit straighter. This is the answer. Oh man, my drawing is terrible. There we go. 0.9 meters per second. As you can see it, too small. So that's how we approach this problem. What we did here was we had a collision of two balls. We knew that the momentums have to equal each other, and so we looked at the y and the x direction. We could have looked at the x first, but I have a feeling that would have kind of just swirled us around and not really given us anything useful, at least at that point. So we looked at y first, and that gave us an idea of which speed had to be bigger. We then used some of the data from the y, used some of the data from the x, i.e. we had two equations, two unknowns, and we used those two equations and two unknowns to solve then for the final speed of the red ball, which I called ball number 2. We could also go back and now find the speed of ball number 1 coming off, but we're fine with this. So that's how this problem is approached. Let's look at the next one. Two blocks of mass 1, which is 2 kilograms. Wait a sec, I should be writing this up. So zoom in. So we have 2 kilograms. Nope, that looks like an R. One of those Russian R's. That sounds like a Y. And then a 5 kilogram right here. And are moving toward each other along a narrow, stationary, frictionless track. Okay, stationary is important because that means that the track itself is not adding momentum. I'm not sure why narrow is important. Maybe that means that they're going to have to collide. Block 1 is initially moving to the right with a speed of 3 meters per second. 3 meters per second. And block 2 is initially moving to the left with a speed of 2 meters per second. All right, so we have a small but fast and a large yet slow. After the collision, the masses move along the track. Aha! What is the direction of momentum of the system of the two blocks before the collision? Okay, so the momentum is always the same. So momentum initial equals momentum final. Therefore, the fact that they say before the collision is irrelevant. Irrelevant? Not important, because the momentum of the system is going to stay the same. So it'll be the same momentum either way. In fact, we'll probably use the momentum before the collision to find the momentum after the collision. Long story short, light blue. So this will be initial M1 initial V1 initial plus M2 initial V2 initial. This will be the initial momentum, which will be 2 times 3 plus 5 minus 2. We have a minus 2 here because I'm calling this the plus direction, and I'm calling that the minus direction. The important thing is there is two opposing directions, and so these speeds, the 3 and the 2 meters per second, must oppose each other. So we have 6 minus 10, which is negative 4. Is that true? And this will be kilograms meters per second, because that's units of momentum. Big part here is we have a negative, which in this case is to the left. Excellent. If after the collision, block 1 is moving to the left with a speed of 0.5 meters per second, okay? 0.5 meters per second, and we'll assume that the mass is unchanged. What is the speed of block 2? Okay, so we know that initial momentum will be the final momentum, which will be M1 final V1 final plus M2 final V2 final. So from here then we're given that this is negative 0.5, and then we knew this is 3, or we assume that it stays as 3, we assume that is 2, and we're left with this defined, question mark. What is the speed of block 2? Okay, and we know that the initial momentum was negative 4. Therefore, we have, I probably should, there we go, leave that as an equals. This will be 3 times negative 0.5 plus 2 times V2 final. Okay, and we can solve this. This will be negative 4 plus 3 halves over 2. Yep, that seems reasonable. Wait a second, no, that's 5. Sorry, I got the mass wrong of my second block. So this should actually be 5. Block 2 is actually the big one. Okay, so we have on clear negative 4 plus 3 divided by 2 should give us, divided by 5 because it's 0.5 equals negative 1/2 meters per second. And that is it a possible answer? It is. Sorry, just a sec. Let me look at this real quick. I think I messed up right there. So this should be a 2. That should be a 2. So we have negative 4 plus 2 over 2 over 5, which gives us negative 3/5, which is negative 0.6. Okay. It's always the simple things that get you in life. So that's not correct. This is correct. Go to that other little stray purple mark. And there's still another one down there. Outrageous. Yeah. Okay, I'm living with it. No, I'm not. There we go. Whoop. Blue. 0.6 to the left. So watch out for those stray little silliness. Okay, the experiment is repeated, but magnets are attached to the blocks so they stick and slide together. Okay, so this is a completely inelastic collision. Completely inelastic collision on the friction surface after the collision. What is the speed of the two blocks after the collision? Okay, I'm going to clean up some of my workspace here because I think all this data we need or have. I'm going to write up here real quick. Negative 4 kilograms meters per second equals initial momentum. So I'm going to try and use this. So this says initial momentum equals final momentum. Always true. And so we have the final momentum will be mass 1 plus mass 2 times some sort of mystery speed. I'll call that V12. What is the speed of the two blocks after the collision? And we know this is going to be the same momentum as before the collision, which would be negative 4 kilograms meters per second. And using that, we have negative 4 divided by, make sure I get the masses right this time, 2 plus 5, which is 7. So that's going to be, I think this one right here, 571. That looks about 4 divided by 7. 4 divided by 7. 571. Okay. So that one is pretty straightforward. Basically, the tricky part of this question is the magnets cause them to slide together, which basically means completely inelastic, which means you can get this equation where you just combine the two blocks into one single block. Experiment is repeated, but with a small explosive attached to the blocks, such that after the collision, both blocks are moving faster than they were before the collision. Which of the following statements is correct? Okay, so both blocks are moving faster. So we're assuming that Masses are constant. Masses stay the same. That's supposed to be an M with a little constant sign over it. Yeah, terrible. So this is, I'm going to look at this verse this way. So you have 1/2 mv squared. I'll put a 1 there, plus 1/2, probably 1 there too, mass 2 v2 squared. So this is going to be the energy kinetic of the system. So if they're both moving faster, then that means, so all of these are going to stay constant. The 1/2, always going to be 1/2. Mass, those are assumed to be constant here. We're going to assume that the explosion doesn't break off the mass. And the velocity, we know that that both got bigger. And since it's both bigger on both sides, we know that the final kinetic energy will be bigger than the initial kinetic energy because they're squared, so the direction, it doesn't matter. Yes, we know that the kinetic energy of the two-block system is larger after the collision. And I'm going to check the other two just to make sure that they are not also correct. Both the momentum and kinetic energy of the two-block systems are larger after the collision. Not necessarily, because you can have two blocks. So what happened is two blocks came together, and then both blocks moved the same direction. And so the momentum combined and added together. What can happen, though, is somehow this explosion happens, and it goes from this to a situation like this, where they're moving apart really, really fast, but they're moving apart exactly opposite of each other. That would mean that the momentum of the system would be 0 because the two momentums would cancel each other out because they're vectors. And so you can have a very large momentum. You can have a very large speed, but a total momentum of 0. So that is not necessarily true. Momentum of the two-block system, larger after, and then it says, it ignores the kinetic energy part, and it says just the momentum is bigger. Well, that's the one that was our objection to part 2, so that's going to be our objection to part 3 as well. Probably true. I'd like to think that there's explosion, that it would create more momentum, but that's not, we can't guarantee that to be true. This is asking which of the following statements is correct, and that should be read as must absolutely be true, cannot be false. So that's how we go for these ones. It's not too bad. I liked them. All right, let's go on to the next.